All right, our next speaker this afternoon is Kaitlyn Chen. Kate's comes to us from Harvey Mudd College, and she's been working this summer with Trevor. And today she'll tell us about their project together, hunting for post-red supergiants.
Thank you, Gwen, for the introduction. With that, I'll jump right in. So the motivation behind looking for these post-red supergiants is the red supergiant problem. So the red supergiant problem is the discrepancy between observed and modeled red supergiant supernova progenitors. So this graph here shows on the y-axis different observed supernova progenitors, and on the x-axis you can see is the initial mass. So if these stars did what we expected them to do, explode as red supergiants, we would see the trend as shown in the dashed line, but instead we see them along this black line. So this means that even though we expect stars between 8 and 30 solar masses to evolve and explode as red supergiants, we only observe around 8 to 20 solar mass stars to do that. So we wonder what happens to the rest of these stars. We think that they evolve bluewards and thus become post-red supergiants. So my sample is a sample of yellow supergiants towards the end of their lives. As you can see, they're kind of on the upper right of this HR diagram. And we can zoom in and see that they're all around above a log luminosity of 5. So this corresponds to about 20 to 40 solar masses. And again, this is the range of stars that are not found to explode as red supergiants. So 13 of these stars are fast yellow pulsing supergiants, and this is set apart from other yellow supergiants because of their fast pulsations. And so we think that this could be caused by a high luminosity to mass ratio, and that is consistent with being a post-red supergiant. So in order to determine if these stars are truly post-red supergiants, we first looked at the H-alpha line. So we wanted to find the H-alpha in emission, as shown by this peak in the graph there, because this indicates circumstellar material. And so in order for a star to evolve bluewards and become a post-red supergiant, they would have to lose a lot of mass. And this mass is shown as circumstellar material. Another thing we did to characterize our sample was fitting a model to our data. So this orange spectrum here is the original data from Mike. And then the blue is, if we zoom in, the blue is the smooth data. So we smoothed this data to match the resolution of the model and fit a model using Markov chain Monte Carlo simulations. So this black line is from the MCMC simulations. And from this, we could obtain certain atmospheric parameters, including effective temperature, surface gravity, and radius. So the specific model we used was Atlas 9, and it is a single star system model. So it doesn't replicate the spectrum of a star that's in a binary system. And so that's why on the very left here, the data, which is in the blue, isn't quite matching up with the black model. And so this upturn in the blue indicates an OB star companion. So this star is in a binary system. In order to determine for sure that the model is not matching the data, we subtracted the model from the data to get this residual graph. And so as you can see, there's a clear upturn in the blue, and this indicates a binary star. The reason why we're looking at binary stars is because binary companions usually indicate a lot of mass transfer. And this mass transfer, again, could cause the star to lose enough mass and become a post-red supergiant. So with the atmospheric parameters I obtained from the Monte Carlo simulations, I was able to create this HR diagram on the left. So the photometric data was taken from a previous survey, and as you can see, my spectral data was able to detect warmer temperatures and lower luminosities. And so this makes sense as photometric data isn't completely accurate. And to quantify these differences, I created these two histograms. So on the left, this is the difference in the effective temperature from the spectral data minus the photometric data. So since we see that most of the values are positive, or on the right of this red line, that indicates that our sample is able to detect these higher temperatures. And then on the right graph is indicating the luminosity. And So the differences in luminosity were about 20% lower in the spectral data. Generally, these plots indicate that our values that we got from these Monte Carlo simulations were pretty consistent with the photometric data. So I was also able to create the spectroscopic HR diagram. And so this differs from a normal HR diagram as shown previously, in that the y-axis is this inverse flux weighted gravity. So this fancy L is proportional to the luminosity, which is on the y-axis of the HR diagram, over the mass. And as you can see in the spectroscopic HR diagram, all these points are falling below these black lines. And these black lines are Geneva evolutionary tracks, or tracks of the evolutionary status of a star of 12 to 40 solar masses. In the HR diagram, as you can see in the bottom left corner, these points or our stars are consistent for the luminosities of stars of these masses, but then this fancy L, they're clearly lower than these lines. So this indicates that our sample has a low luminosity to mass ratio. And this means, since the luminosity is pretty consistent, that the mass must be high. And this could potentially mean that in binary systems, these stars are mass gainers. And this is perplexing because we would expect them to be mass donors and then lose enough mass to evolve bluewards. Coming back to these fast yellow pulsing supergiants. So we wanted to know if these stars were different than the other stars in our sample. So this graph shows confidence intervals with the first point, the probability of a star being H alpha from the sample, and then the next point, the probability of it being an H alpha and a fast yellow pulsing supergiant, and then the same thing for binary for the entire sample and binary for a fast yellow pulsing supergiant. So as you can see with this gray box on the top, there is no overlap between the H alpha for the sample and the H alpha for the fast yellow pulsing supergiants. So all of our fast yellow pulsing supergiants had this H alpha in emission, which again represents circumstellar material around the star. And that is definitely a unique property, as there is no overlap between these two error bars. In terms of binarity, they were less likely to be or fast yellow pulsing supergiants were less likely to be in binary systems, but it's not very statistically different. As you can see, there is some overlap between the two error bars on the right. So my key takeaways from my research is that the binary fraction, or the proportion of stars in my sample that were in binary systems, is consistent with previous studies in the LMC. So this tells us that our data is pretty reliable. And also, we concluded that there is a low luminosity to mass ratio, and these stars must have higher masses. Coming back to the question of finding post-red supergiants, have we found any? We don't know yet. So further research is needed to establish this evolutionary status of the star. So this includes doing a full spectral synthesis and particularly looking for nitrogen in these stars, because as a red supergiant, they develop a nitrous core. But what we can conclude from my research is that many stars in our sample have this circumstellar material, including all of the fast yellow pulsing supergiants. And this is consistent with our expectations for these post-red supergiants. Thank you.
Great.
Thanks. This is very interesting work. So I had a question about this puzzling finding that the stars are more massive than you expected. Do you have some ideas how that could have happened?
So binary systems are very tricky, and of course, we're not entirely sure why yet, and we need to do further research for that. But it's possible that these stars are in triple or more than 2 star systems.
Thanks.
Thank you, Kate. Very nice talk. I was actually curious, so for the stars that actually sit low on the spectroscopic HR diagram,
Mhm.
what fraction of those are binaries? Is it consistent with most of them being binaries? Do you know?
I'm not entirely sure of the exact number, but as you can see, a lot of them are in so binaries is indicated by either
The outline.
the outline. The purple ones are potentially in binary systems, while the black ones, I definitely confirm that they are. So as you can see, most of them do have an outline. So
Very interesting. Any other questions for Kate?
Hi, thank you for the talk. I was wondering whether it can make sense to fit two stellar spectra at the same time for the binaries. And if it does, do you expect it to change the derived parameters that you got?
yeah, that's a really good question. So since these stars are very massive, they're dominating most of the spectrum. So even if we did fit two stars to it, it wouldn't change our values that much. So
All right, let's thank Kate again.